Recovering and simulating pedestrians in the wild. In order to test self-driving vehicles on safety-critical scenarios, we need to perform closed-loop simulation. As the SDV performs a maneuver, we must simulate the new sensor data it observes based on its updated pose. Realistic sensor simulation requires a good 3D mesh representation for vehicles, cyclists, and pedestrians. Current sensor simulation systems, such as CORL, manually design and animate these assets by hand. This approach is expensive and time-consuming and has limited diversity. To truly reconstruct realistic assets at scale, we need to leverage real-world sensor data captured in the wild. Previous asset generation work, such as LiDAR sim, performs simple point cloud aggregation for rigid vehicle objects. This does not work for deformable objects that need to be animated. In this paper, we tackle pedestrian shape and pose reconstruction in the wild. But this is challenging. We need to ensure our approach can handle pedestrians at distance and with different lighting changes, with self-occlusion or items, and with large variations in shape and pose. Previous in-the-wild reconstruction approaches only use images, which can produce inaccurate shape due to ambiguous information. Additionally, past work requires expensive 3D scanning of hundreds of people to construct the body model prior. Instead, in our work, we propose to leverage both LiDAR and camera data captured in the wild by a fleet of sensor-equipped cars. Our method, LIME, is a self-supervised deep structured energy model that directly recovers human shape and pose from sensor data. Importantly, our method is cost-effective and scalable, as we don't use any 3D pose or shape for ground truth, and we only use a single template mesh for our body model. Essential to our method working with a single template mesh is our use of an enhanced linear blend skinning model to represent our shape prior. While past work used learned simple body model parameters, we instead enhanced the LBS template mesh with learnable bone scale factors and per vertex deformations to capture the full range of poses and appearance. We now need to use the in-the-wild sensor data to predict our body model's parameters. We first use a fusion network that fuses LiDAR and image data together to predict the initial estimate, which we then refine through energy minimization. Our energy formulation exploits a raycaster that encourages the reconstructed mesh to agree with LiDAR, reprojection consistency with 2D image joints, and human shape and pose priors. Importantly, we do not require ground truth pose or 3D shape, as the fusion network is self-supervised through the energy formulation. We now show results. Compared to state-of-the-art image-only models, LIME achieves better performance on mesh reconstruction and pose estimation metrics. LIME performs well because we incorporate multi-sensor data. LIME with LiDAR alone significantly improves mesh reconstruction over image, and using both further improves results, especially when incorporating energy minimization. We now show qualitative examples. The top row shows the cropped input camera video and LiDAR point clouds, and the bottom row shows the estimated reconstruction projected onto the image and in 3D view. We accurately capture a diverse set of poses for pedestrians, such as different variations for walking and running, as well as different behaviors while standing. We also capture women, men, and children of different heights and body shapes. With our new bank of pedestrian sequences, we can apply motion retargeting to reanimate the pedestrians in a new scene, and then use a sensor simulation system to evaluate autonomy systems. We use a high-fidelity LiDAR simulation system, LiDAR sim, to reconstruct urban city scenes and simulate sensor data for pedestrian scenarios. Using LIME assets in LiDAR sim, we can perform data augmentation to significantly boost pedestrian detection performance for models trained with both small and large amounts of real data. Here we show reconstructed pedestrian scenarios and the simulated LiDAR. On top is the simulated LiDAR, and on the bottom is the virtual scene. The green boxes are pedestrian detections. The detector model, trained only on real data, processes the simulated data well. Our reconstructed pedestrians can be used not only for evaluating perception systems, but also as training data. Here we show detection results on real data for our perception algorithm trained only on real data on top, and only simulation data on the bottom. The detection models for the models both match well. In summary, we propose LIME to recover and simulate pedestrians from real-world data. LIME generates pedestrians at scale in a cost-effective manner, and we demonstrated LIME pedestrians have improved reconstruction and are useful in simulation for autonomy system evaluation. Thank you.